Hi people and welcome to this video. In this video, we will be working on the trigonometry section of the November 2025 Paper 2 Mathematics exam. Okay, so we're looking at question 5 and 5.1 says, it is given that tan 50 degrees is equal to k. Immediately they give you an equation like this. You know that this is going to be a trig diagram. Okay, so we're going to have to draw our diagram. And they tell us to express each of the following in terms of k. So the first question is we need to express this cos 40 degrees in terms of k. Okay, do not worry that they gave you 50 degrees here, but then they're asking you something with 40 degrees because 50 degrees and 40 degrees, if you add them, they give you 90 degrees. So you know that these are complementary angles, meaning they are just using cofunctions. Okay, so let's go ahead and draw our diagram down first. So our diagram with this, because we have tan 50 degrees, our angle, do you see that it is an acute angle? This is an angle greater than 0 degrees, but less than 90 degrees. And so it lies in the first quadrant. And so when you measure it, we just have 50 degrees over here like that. So this is 50 degrees. And then we'll draw our line down to the x-axis, which is of course perpendicular to the x-axis. Okay, and so what they tell us is that tan 50 degrees is equal to k. So using our acronym SOHCAHTOA, remember that with tan, we take the opposite side over the adjacent side. So when they say tan 50 degrees, yes, 50 degrees is equal to k. If you express this as a fraction, okay, k actually has a natural denominator of 1. And so what that means is that k is the opposite side and then over the adjacent side. 1 is the adjacent side. So let's go ahead and put those down first. So 50 degrees is here. The side opposite 50 degrees is k. So that is k. And then the side next to 50 degrees is 1. And all we need to find is the hypotenuse. Because this is a right angle triangle, we're going to use Pythagoras to find this. And so we'll call this radius, okay, r. So I'll say to find r, we say r squared is equal to, so using the theorem of Pythagoras, is equal to k squared plus 1 squared. And now we just need to solve for r. So at this point, you can go ahead and solve for r by getting rid of that squared, and we need to square root both hand sides. Yes, we considered a positive or negative solution, but r is a radius, so it's always going to be positive, okay? And also everything here is positive because it's in the first quadrant, okay? That's positive, okay? The x value is positive. The y value is also a positive value. Okay, so now square root r is equal to the square root of k squared plus 1. And that's what we have there. R is the square root of k squared plus 1. And now we can find what they asked us to find. Cos 40 degrees. So we have 50 degrees here and all the other sides. With 40 degrees, you can do this in two ways. You can either decide to use cofunctions, okay, or you can actually just find this angle over here. The angles in a triangle add up to 180 degrees. And so 50 degrees plus 90 degrees plus 40 degrees give you 180 degrees. Let me just change that to blue instead. And now we can find cos 40 degrees. So cos, using SOHCAHTOA, we take the adjacent side over the hypotenuse side. And so we're going to now look at 40 degrees specifically. Okay, this would be the side opposite the 40 degrees. But then next to 40 degrees, adjacent 40 degrees, that is the k. Okay, so adjacent over hypotenuse is k over the hypotenuse, which is this. And so our answer is k over, and we have the square root of k squared plus 1. And that is our answer there. Moving on to the next question. The next question, 5.1.2, we have this expression and you can already see it has a very suspicious angle, 25 degrees, which we know is half of 50 degrees. Okay, so we're still working with 50 degrees really, but then, we have to find a way to express this so that it says 50 degrees and then we can actually express it in terms of k. Now, with the way this is, it says 2 sine 25 degrees cos 25 degrees. You can clearly see we are using double angles. Okay, so let's just go ahead and put down the double angle identities. Okay, so here we are. And you can already see from this that they have clearly used the double angle identity for sine 2a here. Okay, so this is 2 sine 25 degrees. So you can see that A here represents 25 degrees. So we can express this as sine 2, and then you can see A is 25 degrees. So that's 25 degrees, sine 2A, over, and look at what we have here. We have a negative 2 and then positive 4 sine squared 25 degrees. Clearly, there's already a common factor of 2 or negative 2. We'll have to decide. Now, this one is one that looks a lot like this identity. Cos 2a equals 1 minus sine squared a. The only difference here is here, this first number is positive, and then this with the sine squared a is negative. And then here, this is negative, but then this is positive. So what it means is, yes, there is a common factor, but that common factor is negative. So between negative 2 and 4, we can see what is common is actually negative 2. And then when we take that out, what are we left with? If you say negative 2 divided by negative 2, you get 1. Positive 4, okay, divided by negative 2, you get negative 2. And then the sine squared 25 degrees. Okay, so you can see clearly that's what they use, okay? Yeah, I see that I wrote that wrong, sorry. It should be 1 minus 2 sine squared a, okay? Okay, so this is what we have. Remember, your formulas are in your formula sheet as well. Okay, so now let's simplify. We have sine and then 2 times 25 degrees. That is 50 degrees that we have there. And there, see, it's in terms of 50 degrees. We can actually express this in terms of k. And then the negative 2 and this, you can see that this is the identity for cos 2a. So this becomes cos 2 and the a here is 25 degrees. So times 25 degrees. Let's find the value of sine 50 degrees. So 50 degrees is over here. And sine, using SOHCAHTOA, we take the opposite side over the hypotenuse. So that is the opposite side over the hypotenuse. Okay, so that is k over, so it's basically this, k over k squared plus 1. Okay, because we already have that as a fraction, what we can do is, instead of saying over, we can just use a division sign. So we can say divided by, and then we have this divided by this, negative 2. And then what is this? This becomes cos 50 degrees as well. Okay, so I'll just rewrite this first. And now we need to find the value of cos 50 degrees. So this is negative 2 and then cos 50 degrees using our diagram. Here's 50 degrees. Cos, we take the adjacent side over the hypotenuse side. So the adjacent side, that is the 1 over the hypotenuse, which is that. And so we just say this is 1 over, okay, see, these are multiplying since they're next to each other. And so they're just going to become a negative 2 and then over that denominator of root k squared plus 1. Now we are dividing. When you're dividing by a fraction, what we can use is this rule, tip and times. So it means that you're going to tip this number, only the number that you're dividing by. So keep this as it is. And then we are going to tip this number. So you're going to swap the numerator and the denominator. So it now becomes the square root of k squared plus 1 over negative 2. And then the times part is change the division to a multiplication. Okay, so this is what we have. You can see that when multiplying, okay, so when you look across, if you find anything that is the same, they will cancel, okay, because you're going to say this times this, so they end up being together in the numerator. And then that times that, and they end up being together in the numerator, and then they will cancel like that. Okay, so you can just straight away cancel them. And so this is equal to simply k over negative 2. And that is our answer. K over negative 2, you can also express this as the coefficient in front of k, that is just an invisible 1. So this is actually a 1 over, or negative 1 over 2, and then k. Okay, so you can write it like this, or like that, it's fine. And that is our answer. Moving on to the next question. And then we have 5.1.3. We need to express sine 10 degrees in terms of k. Okay, 10 degrees, it seems like an unusual one, but just keep in mind that you're always trying to express everything or all the angles, right? Either as 50 degrees or 40 degrees. And here's our advantage here with 10 degrees. 10 degrees, okay, if we use cofunctions, remember, the angles with your cofunction identities, they're going to always add up to 90 degrees. Okay, for example, if you have cos 40 degrees, this is exactly the same thing as sine 50 degrees. They have the same value. So we can use cofunctions on this And we're going to find a 40 degrees in here because of 80 degrees. You know that 10 degrees plus 80 degrees gives you 90 degrees. And so if this is sine 10 degrees, we can express it as, and so if this is sine 10 degrees, you can express it as cos 80 degrees, okay? A more gradual way to show how that works, or more step-by-step approach would be to just take this as sine, and you're basically saying 90 degrees minus what gives us 10 degrees, and that's minus 80 degrees. And so using cofunctions, remember how sine 90 degrees minus theta is equal to cos theta. In the same way, this is equal to cos 80 degrees. Okay, grade 12, so make sure to study your cofunctions. That is actually one that I don't think they put in the formula sheet. Yeah, that's not in the formula sheet, so just make sure to study those formulas, okay, or identities. So this is what we have, cos 80 degrees. So here's what we can do with this. Cos 80 degrees can actually be expressed in a way that it has 40 degrees because 80 degrees is double of 40 degrees. So this is actually cos 2 times 40 degrees. And so we are actually just using double angles to express this. So right now we can't express it as k because it's still 2 times 40 degrees. It's not cos 40 degrees. So you can't change it to something that has 40 degrees only without a 2 in front of it. And so that would be to expand it to one of its double angle identities. Okay, so you can see how we can just simply use that. Honestly, you can use any one. I'm just going to go with this. But it's unnecessary because it's not like I have the value of this, but I'll just go with it. Okay, so at this point, now we can just expand this. We can make it equal to one of the double angle identities for cos 2a. Okay, so with this, I'm just going to go with this one. Okay, 2 cos squared a minus 1 because, yeah, I just feel like this would be simpler to work with. Okay, the one reason it's nice to kind of use this one is because it has cos squared a. We already know what cos a is. Okay, we know what cos 40 degrees is. That is this. So I'll just take one that already has that. Okay, so that is, we're going to rewrite it as this. Okay, so this is what we have. And so we're saying cos 2 times 40 degrees is equal to, and that is going to be 2 cos squared, and then a, that is 40 degrees, okay, because this was 2a, so this is a, minus 1. And we already know what cos 40 degrees is. So this is simply to multiply by, and of course it's cos 40 degrees and then all squared. So that is still squared and then minus 1. So let's just find out what cos 40 degrees is. Cos 40 degrees, we already found that to be this, k over k squared plus 1. So in place of this, we're just going to put that in. So this is k over the square root, the square root of k squared plus 1. And just simplify. Okay, so the 2 is still there. We're going to square those. The numerator gets squared to become k squared. So it's just k squared over the denominator gets squared. And that square root is going to break open. Okay, so those would cancel each other out. And so we'll have k squared plus 1 and then minus 1. Okay, so the 2 and the k squared, they're going to multiply, numerators multiply to become 2k squared and then minus 1. But they do want us to simplify this. So what we can do is express 1 so that we are able to subtract. When adding or subtracting fractions, you need to ensure that the denominators are the same. So you can put this over 1, and then what will make the denominators the same? Clearly just to multiply numerator and denominator by k squared plus 1, or you're just expressing it as k squared plus 1 over k squared plus 1, because that is still 1. And so now they have a common denominator. This is k squared plus 1. And then in the numerator, what we have is 2k squared. And you're saying minus this. Okay, so you can't just say minus and then all of this, because what happened here is you had a minus and it was just a minus 1. But then we changed that 1 in the numerator to something that has more than one term. So what we could have really done is just put brackets around this to show that. Not really necessary, you just have to show that here. So when you say minus, you need to say minus k squared plus 1. And now we can simplify that. So this is 2k squared minus the k squared, and that becomes a minus 1 over k squared plus 1. Okay, so this is what we have. And this is 2k squared minus k squared, which is k squared, then minus 1 all over, and we have k squared plus 1. Okay, so this is what we have. I would have tried to factorize that numerator, but there's no use because the denominator is not a k plus 1, it's a k squared plus 1. So, we can't really get any factors here that would cancel because you can't factorize this. There's no such thing as the sum of two squares. Okay, you can't factorize. There's no factorization method like that, but there is the difference of two squares. So at this point, this is our answer. And that is it for that question. Moving on to the next question. Question 5.2 we have given, and we've been given this expression, and we need to simplify the expression above fully to a single trigonometric ratio. Okay, so with the expression, do you see that in some places we have angles that are greater than, not some places, just this, okay, greater than 360 degrees, and here an angle that is negative. So here is the rule that you can follow for this. If your angle is greater than 360 degrees, what you're simply going to do is subtract 360 degrees from the angle until it is below 360 degrees. Okay, it shouldn't be negative, just below 360 degrees. And then if your angle is negative, okay, less than 0 degrees, what you're going to do is add 360 degrees to it. Okay, so this one is 540 degrees, which is already greater than 360 degrees, and then plus x. So we're going to minus 360 degrees from that. So with that, we're going to have sine, and then just say, then 540 degrees minus 360 degrees is 180 degrees, and then plus x. Okay, and now you can see we can simplify that using our reduction diagram. Okay, so multiply by, and we have cos 90 degrees plus x. That is clearly cofunctions. Remember your cofunctions? So this simply simplifies to negative sine x. Okay, and then we have all over, and then sine negative x. Grade 12s, please be careful here. Don't make the mistake of just saying, oh, okay, it just goes there. Okay, the negative just goes in front of it. That is not true, okay? And if they ever gave you something like cos negative x, you will get that wrong because you'll just take that negative and put it in front. Remember, the angle there is negative. All you have to do is add 360 degrees. If you do that, look at what happens. This is now going to be plus 360 degrees is going to be a positive 360 degrees minus x. This can be reduced. Okay, so now we can just reduce using our reduction diagram. Okay, so this is equal to, we have sine 180 degrees plus x. And so 180 degrees plus x, you can see this is in tans quadrant where sine is negative. So this reduces to negative sine x. And it's multiplied by negative sine x. And then all over, we have sine 360 degrees minus x, which is also not in sine's quadrant. It's in cos's quadrant. And so sine is negative there. So that simply just becomes negative sine x again. So the negative times the negative give you a positive, and you have positive sine squared x in the numerator and negative sine x in the denominator. Sine x and sine x cancel in the numerator and denominator. And so all we have left is, there's still a negative here. So it is negative sine x, because sine x divided by negative 1. And that is our answer. Moving on to the next question. The last question for question 5 says, hence, determine the values of x in the interval where x is, okay, so it's going from 0 degrees to 360 degrees, for which, and they take the expression we already had, and now they just put a square root. So for which this will be real. Okay. Okay, so we can just work with a simplified form of this. We know that all of this, and I'll just write it again. We know that all of this simplifies to negative sine x. So we simply need to find the values of x for which the square root of negative sine x is real. Okay, so negative sine x. Okay, so because we have a square root here, you know that if you square root a negative number, it will be non-real. Okay, so let's just look at how we can manipulate this. Okay, so let's see which values of x will make this real. As long as this, okay, ends up being a negative value, given as a negative value, then if you say this negative multiply by this, it's going to give you a positive because this ends up being negative, of course. So you're saying a negative times a negative gives us a positive. So what is under the square root, what is under the radical, must stay positive. So let's just find out the values of x for which this will be negative. Okay, sine x will be negative. And then that would be, the values of x for which they're going to be real. Okay, so with a sine graph, the sine graph looks like this. It just goes up and then like that and then curves right like that. Okay, and then from 0 degrees to 360 degrees, that is 0 degrees, that is 180 degrees, and this is 360 degrees. We can also look at in between, but in this case, it's not really that necessary. You look at 90 degrees and 270 degrees. So this is the y equals sine x graph. Okay, that part. With the y equals sine x, where is it negative? Where does it have negative y values? So the y values are found on the y-axis. If you take a point on the graph and you map it to the y-axis, you can see the y value it has. This has a positive number, whatever that is over there. Okay, if it was at 30 degrees, it would have a positive a half. And we're looking for where the graph of sine x is going to have a negative value. And you see that would be all through here. Okay, so in other words, what we're saying is sine x needs to be less than 0. It needs to be negative, and then of course you'll say negative this times whatever negative value that gives us. Okay, it has multiple negative values, and then it will give us a positive value, and the square root of a positive number will be real. Now, I want to say less than or equal to 0, but the thing about equal to 0 is if you make this, okay, the value of sine x equal to 0, for example, here, see the denominator, this is sine negative x. We knew that, okay, when we simplified, it simplified to negative sine x. So if that becomes 0, okay, so it's going to be negative sine x, and if sine x is ever equal to 0, this is just going to be minus 0, which is just 0. And then it just makes this undefined. They want the values of x for which it's going to be real. Real numbers are numbers that you can find on a number line. Undefined, it's undefined. You can't find a value like that on a number line. It doesn't even really have a value. So we can see all the places where it's going to have a negative value, which is what we're looking for. And you see if you line it to the y-axis, that's a negative number. That is a negative value all through. Okay, so you can see that where sine x is negative is all through here, all of these x values, which are values that are greater than 180 degrees, but less than 360 degrees. And that would be our answer. We would say that x is simply greater than 180 degrees, but less than 360 degrees. Okay, I can't say equal to 180 degrees. Okay, I can't say greater or equal to 180 degrees because at this point, do you see that the y value of the sine graph is 0? And I don't want that because it's going to be undefined. So that would be our answer over there. And that is the final question for question 5. And that is it for question 5. And moving on to question 6. We are now on question 6, and 6.1 says, prove that, and we have this on the left-hand side, and we need to prove that it is equal to this on the right-hand side. Okay, we can actually work with the left-hand side and work it to get to the right-hand side, because you can see these have been factorized. Okay, so this has been simplified. Okay, so I'm going to go ahead and rewrite that left-hand side. Okay, so this is what we have, and we're trying to prove that this ends up being equal to that. So the one thing that is very noticeable would be this negative cos x. So how would they have gotten that? So right now we don't have any fractions, but do you see how tan 180 degrees minus x, if you reduce this using the reduction diagram, this will become negative tan x, because 180 degrees minus x, that is sine's quadrant where tan is negative. So this becomes negative tan x, and then we're still multiplying by this. I don't want to change it yet because I'm not really sure what they're doing. I think if we kind of like distribute out here, we'll see what exactly they did. So I'm just going to leave it like this and then say multiply by 1 minus cos squared x and then plus cos squared x. Or let's just see. Okay, because this is clearly going to become, so it's tan x, it's going to become sine x over cos x. And so we can leave that cos x with a negative. So the denominator stays negative. And so this is what I mean. We can actually change that. But let me just do this step by step. So we have negative tan x, which should be negative sine x over cos x. But I'm going to leave that negative in the denominator. So I'll leave this as sine x over the cos x, but then leave the negative here. And then we have multiply by 1 minus cos squared x and then plus cos squared x. I will change that, but I just want to see how they did that. So you can see we got the negative cos squared x. That's fine. But then, what did they do to this? If we distribute out here, let me just do that in another color. You're going to get the sine x times the 1. That is just sine x. Okay, and then if you multiply with those, that is a positive sine squared x and then cos x. Okay, so I need to see how do we create that. And then of course, if you multiply there, that's a negative cos x. And if you multiply there, that is a negative sine x. Okay, makes sense now. Cos squared x. See how this is sine squared x cos x, and this is sine x cos squared x? It's because they actually did change this. Okay, look at what happens here. If you say sine x and you distribute this in, that becomes sine x. This becomes negative sine x cos squared x, which is one of the things we will definitely have here. Okay, so this ends up changing. So cos squared x, it has an identity, and we can actually change it to this. Remember how sine squared x, and I should just write this in another color so it doesn't confuse. Sine squared x plus cos squared x is equal to 1. You can make cos squared x the subject here. So cos squared x is actually equal to 1, and then transpose the sine squared x. And there we go. So that's what that is equal to. So straight away, I'm going to change this to 1 minus sine squared x. And now at this point, I'm realizing that if I leave it like this, it's not going to make any sense. Here's what they did. You see that these two, they are different fractions, okay? Terms are separated by plus or minus signs. So right now, looking at this, how many terms do we have here? Remember that brackets, okay, multiplication, they join terms together. So we have a plus here. That is what is separating this. We have two terms, okay? So this is just one term alone. It doesn't have the same denominator as this term. So we need to give it a denominator of negative cos x as well. Okay, and so to do that, you can put this all over 1 and then just multiply its numerator and the denominator by negative cos x. And there, this is where all of that comes from. Okay, so let's just simplify and we're going to multiply out here. So this is going to be the sine x, and then we can just, group it the way they did, because clearly this came from grouping. Okay, they factorized it by grouping them, and then they were able to find the common factors. So we have sine x, and then we multiply in here. This is negative sine x cos squared x. And then over here, what we have is, I know there's a plus here, but you can just see it as, let's just say we move this to this side. We are multiplying, okay? So it's actually a negative cos x because, positive times negative is negative. It's a negative cos x, okay? And then multiply by the 1 first. And so that gives you a negative cos x. And then negative cos x times negative sine squared x, which gives us positive sine squared x cos x. That's what happened there. Okay, and then it goes all over because they both have the same denominator and we are adding these fractions. Okay, I already simplified that. We're just going to write them all over the same denominator of negative cos x. Okay, let's just see, is this what we have there? We've got our sine x, our negative sine squared x cos x. Okay, you can see that these two, they should be put together. So I'm going to rewrite this as the sine x and then put that here, positive sine squared x cos x. And then we need to put the minus cos x and then of course the negative. Okay, so this is minus cos x and then minus sine x cos squared x and then all over negative cos x. And now we can factorize. Okay, so with the way that worked, I was able to expand it because clearly they grouped things together. They grouped it together as it was like this already. We can also just see that there are 4 terms and we have common factors between the pairs. So this 2 gets grouped together, this 2 gets grouped together. And so we have this is equal to, and what is common in the first and the second term in the first bracket? That would be the sine x. And then what is left? Sine x divided by sine x, that's just 1. And then this divided by sine x, 1 of that cancels, and we have positive sine x cos x. Okay, here, what is common? Just take out what you saw common here. You see that this is a negative cos x. We already have our sine x. Okay, here's our sine x. And this is the minus cos x. So we know immediately we're taking out a minus cos x. And then what is left? This divided by that just gives you 1. And then all of this divided by that. The negatives cancel, one of the cos cancels, and you're left with positive sine x cos x. Okay, so they use grouping here. And then over negative cos x. Then it is finally equal to, how many terms do you have in the numerator? Well, there's the minus here. So it means that this is one term and this is another term. So we have two terms and we can see we have a common factor. Okay, it's the whole bracket, this bracket. Let me just check that I wrote that bracket correctly. 1 plus sine x cos x. Okay, so we're just going to take that out as a common factor. And then what is left? So we have in the first term, if you take that out, we are left with the sine x. And in the second term, you take this divided by this, those cancel, and again you are left with the negative cos x. And there we go. So all over negative cos x. Okay, so you can do that sometimes, like distribute that out so you can see what did they create and then just see how this expression that you have can become that. Okay, so that is equal to the right hand side of that identity, and that is our answer. Moving on to the next question. Okay, question 6.2 says, it is given that sine squared x and then cos squared x and a half sine 2x are the first three terms of an arithmetic sequence. The constant difference of the arithmetic sequence is not 0. Okay, they're clearly saying that for a reason. We'll look into that. And they want us to determine the general solution for x. Okay, so they have given us a pattern, and it is specifically an arithmetic sequence, okay? An arithmetic pattern. And how would we use this to create some sort of equation that helps us solve for x and then, of course, find that general solution for x? Well, the sequence is arithmetic. So if it is a linear sequence, it means that it has a constant difference. They're also telling us something about the constant difference, and we'll take note of what that is, or really how that difference is going to end up being equal to 0, because we must make sure that that doesn't happen. Okay, so to form this equation to solve for x, then given these three terms, term 1, term 2, and term 3, what do you know about an arithmetic sequence? We know that it has a constant difference. Okay, so if you take term 2 minus term 1, right, it's exactly the same as term 3 minus term 2 because that difference is constant. So this is where our equation will come from. So term 2 is cos squared x minus term 1, which is sine squared x, and this is equal to, and then we have a half sine 2x minus cos squared x. Okay, but they do say the constant difference of the arithmetic sequence is not equal to 0. So let's go ahead and just make sure that we put that down. So you know when you're solving for a trigonometric equation, right? And there is a case where you have the denominator, okay, and it has a trig expression there. You must ensure that that is not equal to 0, okay? So it won't be undefined. In this case, they are giving you a restriction. So this is a restriction and we need to go ahead and just take this into account. Okay, so let's look at that restriction. They said the constant difference should not be equal to 0. So D should not be 0. And how we find the constant difference here was, term 2 minus term 1 and term 3 minus term 2. So that means these, they represent the constant difference. None of these must be equal to 0, meaning cos squared x minus sine squared x should not be equal to 0. In the same way, a half sine 2x minus cos squared x should also not be equal to 0. And we will keep that in mind. Okay, so let's see how we would solve for x in this equation. So, okay, we have x, we have 2x. We wanted to stay just x so we can solve for x eventually. The thing about it is you can either change it to 2x, but then everything needs to have 2x. So you can actually solve for x there, or everything needs to have x. Right now we have things with x, and then we have something with 2x. So this needs to change. So I'll leave this as, and I can already see like terms, but let's change that first. We have cos squared x minus sine squared x, and then is equal to, this is a half, and this is sine 2x. We can use the double angle identity for this, which is 2 sine x cos x, and then minus, of course, cos squared x, which I feel like I should have just taken over at this point. Okay, let's go ahead and start transposing. So we have a cos squared x. This is like terms with it, so we take it over and it will become positive cos squared x, giving us a 2 cos squared x. And then we have a minus sine squared x, and then here these multiply. If you say a half multiplied by 2, 2 is just over 1. So the numerator and denominator would cancel each other and they become 1. So this is just sine x cos x. Okay, I can see that this is going to become a trinomial. Let's just take this over. So this is 2 cos squared x. And then we can take this over. So put this in the middle because this will be the middle term. It's minus sine x and then cos x, and then the minus sine squared x. Okay, so the cos squared x is here, the sine squared x is here, and then the one with both sine x and cos x is in the middle. And then is equal to 0 because there's nothing left on that side. Okay, so at this point, we can factorize, and it's really just like factorizing a trinomial. Say sine x, right? Let's call this a, and cos x, let's call this b. If you had to rewrite this equation, it's going to be 2b squared, okay, because cos x is b, and then minus, and this is a, b, and then minus a squared. And how would you factorize this? This is one of those where you can see that this 2 here is not a common factor all through. So I'm going to use the cross method here. So I'll take the factors of the first term, which is 2b and b. So 2b and b, okay, they give you 2b squared. And the factors of the second term, a squared, okay, it's negative a squared, but I'll say a and a. Now, I know it has to be negative. One of them has to be negative. But to decide which one, remember that when you cross multiply, and that's why it's called the cross method, when you cross multiply and then add your numbers, okay, your products, then the answer you get there should be the middle term value here. So before giving a negative to any one of them, I'm just going to cross multiply first. So 2b times a is 2ab, and then b times a is ab. Okay, so which should be negative here so that you end up with a negative ab? You should give the negative to the 2ab, okay? Because negative 2ab plus ab gives you negative ab. And there we go. And so now I know that what should get the negative is whatever created the 2ab, which is a 2b times a. So that takes the negative, that takes the positive. So you see how this ends up factorizing to 2b plus a times b minus a. And we know what b and a stand for. And so now we can just fill that in. So that means when you factorize this, b, remember that's cos x, that is just 2 cos x, and then plus sine x, and then open a bracket, and then there's b again. So that is cos x and minus sine x, which is equal to 0. Okay, so that makes it less intimidating. Of course, you can factorize it with it just being with cos x and sine x. That's perfectly fine as well. But if it does feel intimidating, you can do that. Okay, so this is what we have so far. And we're still trying to solve for x in this equation and see what we have. So we have this multiplied by this is equal to 0. The only way this is possible is if the first bracket was equal to 0. So you said 0 times that and then gives you 0. Or if the second bracket was equal to 0 and you said this times 0 and then you got 0. But I'm seeing something interesting here, which is this cos x minus sine x. Look at that. Remember how we said that cos squared x minus sine squared x should not be equal to 0? That means there's something here. There's a solution here we're not going to accept. So here's the thing with this, right? If you have to take this and you take it further, you factorize it, look at what you're going to get. This is a square value. This is a square value. There's a minus in the middle. We can actually use difference of two squares to factorize this. So this is going to be cos x minus sine x multiplied by cos x plus sine x using difference of two squares. We know that this should not be equal to 0. You see the problem here? If we are trying to solve for x and we know that for this to be true, then of course 2 cos x plus sine x, right, should be equal to 0. Or this cos x minus sine x is equal to 0. You see how that contradicts this? We said that this cannot be equal to 0. Once you factorize it, you can see this part, okay? That shouldn't be equal to 0. So if you were trying to solve for x here, you'd also say this is equal to 0, or that is equal to 0. But we know this cannot be equal to 0. And so we need to actually just tell them. But do you remember that you said the constant difference cannot be equal to 0? Therefore, the difference, which was equal to, ended up being equal to cos squared x minus sine squared x. That cannot be equal to 0. Okay, it should not be equal to 0. Of course, just write that in a more, in a better way. I guess you can just write it as that cannot be equal to 0. The difference specifically. Okay, so you see what we can't accept. We can't accept that because of their restriction. Okay, so we will not take that answer and we'll simply say 2 cos x plus sine x is equal to 0. And this is what we're going to focus on. Okay, I'll just conclude here. Therefore, cos x minus sine x is not equal to 0. And we'll leave that. Okay, so this is what we're working on. Let's go ahead and solve x. What does this become? Well, we have cos, you have sine. You can clearly create tan. Okay, so in this equation, how do you create tan? Remember how tan x is equal to sine x over cos x. It means we need to leave sine in the numerator. So leave this and take the 2 cos x over. So we have sine x is equal to, that becomes negative 2 cos x. And now we can go ahead and divide both hand sides of the equation by cos x, so that we have sine x over cos x. So divide by cos x, and finally what we have here is tan x is equal to negative 2. This is what we need to find the general solution for. Okay, so find the general solution for x in this equation. Okay, it's tan, so it's very simple. You can use that whole table method and ask yourself, where is tan negative? I find that unnecessary, so I'm going to use the quick method here. And you can check out this video to see the 2 different methods that I'm referring to here. Also, please note that in tan, okay, when I was recording it really late. I accidentally said you have to add 360 degrees. No, okay, you have to add 180 degrees. And that was pointed out by someone in the comments. And I did correct that and pin it to the comments. So just make sure you check that. Okay, but anyways, we are still going to speak about that here. So when solving for x here, what we're going to do is first find the reference angle. Okay, so our reference angle would be found simply by transposing tan. So you're using the second function of tan. When it comes over, it becomes the second function. So shift tan and then of negative 2. So this is the difference between that table method when you ask yourself, is tan going to be positive or negative in this quadrant? In this case, you don't have to say shift tan of positive 2 and then start considering the quadrant. You can just say shift tan negative 2 and get your reference angle. So right now, reference angle is negative 63 point. And it is, I'll just go ahead and round off because it's just tan x, it's not tan 2x. We don't have to divide at the end of the day. So we can leave it as 63.43 degrees. Okay. And now we can solve for x. So with the tan graph, it's very simple. You don't have to consider different quadrants. You're simply saying x is equal to whatever your reference angle was, which was negative 63.43 degrees. And then you're saying plus k of 180 degrees because the tan graph repeats itself every 180 degrees. And of course, where k is an element of integers. Okay, so at this point, if you wanted your angle to be positive and not negative, this is where you're going to add something. So here, the angle is just negative just because of the position of this angle. If you looked at it on a graph, you know what the tan graph looks like. It goes up like that, and then you have an asymptote and it goes like that. Okay, it completes one cycle from 0 degrees to 180 degrees. Okay, and then before this, you're also going to have another tan graph. Okay, from negative 180 degrees to 0 degrees, you have a tan graph like that, goes up, reaches an asymptote, and then goes like that again, and it just keeps repeating like that infinitely. And so what is going on here is when we're trying to solve for x in this equation, when you say tan x is equal to negative 2, you're saying, where does the tan graph have a y value of negative 2? So negative 2 will be maybe somewhere here, right? Where it has a y value of negative 2. On the negative part, where the angles are negative, that's here. Okay, so that's negative 63 point, you see? And that makes sense because the asymptote will occur at negative 90 degrees. And then this is where it has a y value of negative 2. Then this answer will repeat infinitely. 180 degrees later, since the tan graph repeats itself every 180 degrees, it's going to have the same y value of negative 2. And so here's how you catch that positive solution. If you end up getting nervous because maybe you finally got the memo and you're practicing now, and then you see that their answer is positive, don't panic. All they did is they used a different method, but how you can get to their answer is simply by taking this negative answer and then telling yourself, I know my tan graph repeats every 180 degrees. So to get the positive value that they would have gotten, I'm just going to add 180 degrees, and that would be your answer. Okay, so if I say plus 180 degrees, there we go. That is probably the answer you will see, and you don't have to panic. So finally, you can just tell them x is equal to 116 degrees, okay, 116.5, and rounding up, it's going to be 57 degrees plus k 180 degrees, because this is a general solution. So this is the infinite solution, basically. The answer where the graph tan x is always going to have a y value of negative 2 all through from negative infinity to positive infinity. Okay, so you can leave your answer like this. And that is our answer there. And that was the last question for question 6. And that is it for question 6. We are now on question 7. And question 7 says, in the diagram, the graph of f of x is equal to cos 2x is drawn for the interval where x is an element of negative 135 degrees to 135 degrees. Okay, so this is a cos graph. Just always try to spot that shape of the cos graph. Okay, you know that the cos graph from 0 degrees to 360 degrees, right? It's going to look like that. So can you spot that shape here? Okay, here it is. But in this case, it's cut off at this point just because it goes to 135 degrees. It wouldn't end at 360 degrees, first of all, because they put a 2 in front of the x. Okay, so we're going to look at what that does. And the reason I'm just not going into it is because I can see the first question, 7.1, says write down the period of f. Okay, so this is where this comes in. The period of a graph is just really how long this graph takes to complete a cycle. You see with the cos graph, okay, you see that if you look at it from 0 degrees to 360 degrees, this is the shape it makes. And then 360 degrees later, it will have the same shape. So it will look like this again, okay, and it will end at 720 degrees here. And then 360 degrees before this, it will have the same shape again, okay, so from negative 360 degrees to 0 degrees. And so that's how long it takes to complete a cycle. But your graph can be manipulated, and in this case, it has been. So we have cos 2x. They put a 2 in front of the x. When this happens, it means that the period would change. And how you find the period of a graph, you take the old period. You know that the cos graph, as we saw, it completes a cycle in 360 degrees. Okay, so the cos graph has a period, the original cos graph, y equals cos x, has a period of 360 degrees. But then to find the new period, you just say the old period divided by the number in front of x, which is a 2. So divided by 2 is 180 degrees. Okay, so that graph has a period of 180 degrees, meaning it no longer completes a cycle in 360 degrees, okay, like it used to, okay, like that, 360 degrees. It now completes a cycle in 180 degrees, so in half what it used to. So your graph would be squeezed and it will be more narrow. It's not too clear to see here just because of the intervals they've used. Okay, so that is our answer. The period is now 180 degrees. Moving on to the next question. The next question says 7.2, on the same set of axes provided in the answer book, draw the graph of g of x which is equal to tan 2x minus 1 for the same interval. Okay, so tan 2x minus 1. So it also has a 2 in front of it. The tan graph, just remember from the previous question, you saw what the tan graph looked like. Okay, a brief example of what it looks like from question 6, right? It looks like this. So it goes up and then there's an asymptote at 90 degrees. And then comes from being really close to the asymptote and then like that. So it has a period of 180 degrees. But you can see that they put a 2 in front of the x, meaning it's old period divided by that coefficient of x, okay, gives you 90 degrees. And so this graph is not going to look like this anymore. It will be squeezed in. So instead of having an asymptote at 90 degrees, it will have this at 45 degrees. Okay, so you just take all the old angles that you saw here and you divide them by 2. That is, of course, to get this part, okay, the tan 2x. But then we also have a minus 1. So with the minus 1, that graph, okay, you're just taking tan 2x, all of those y values, and you're saying minus 1. So it will take the graph and it will shift it 1 unit down. So I think it's actually important that I just show the rough graph, okay? So at 90 degrees, remember the asymptote will not occur at 90 degrees. It's going to occur at 45 degrees. And then it's not going to end at 180 degrees. It's now going to end at 90 degrees. So all those angles that were there, just divide them by 2. And this is somewhat what your graph is going to look like. Okay, so what we can do is just look at what the original one looks like so we know what the manipulated one would look like, what the graph of G looks like. There are other special points that you need to pay attention to, and that is where the tan graph has a y value of 1, okay? On the graph y equals tan x, okay, the original graph, it has a y value of 1 at 45 degrees. So you know now the new graph will have a y value of 1 at half of this. We'll see. We'll just put down things that actually show up there. And then where it has a y value of negative 1, it will have a y value of negative 1 at 135 degrees. Okay, so the new graph would have that at half of this. So I'm just going to put this on the side and let's put down our graph. Okay, so this is what we have and let's just plot down. So at 0 degrees, we can start at 0. Tan 2x, just the tan 2x part, it's going to have a y value of 0 because if you say tan 2 and then substitute 0 there, okay, times 0, you're just going to get 0. But then when we say minus 1, we're going to get a negative 1, okay? And then at 45 degrees, what do we have here? You see that the graph of tan 2x, because all our angles get divided by 2, do you see that previously we had an asymptote at 90 degrees? You're going to take that angle divided by 2, and now you're going to have an asymptote at 45 degrees. So this is where our asymptote will be, and it's going to be a dotted line. Okay, because the asymptote is at 45 degrees. At negative 45 degrees, there would also be an asymptote, just like with the graph y equals tan x. At negative 90 degrees, there's an asymptote there. And then at 90 degrees, so the original graph has a y value of 0 at 180 degrees, but you're going to say 180 degrees divided by 2, which is 90 degrees. And then this is where it will have a y value of 0. But then, of course, we have a minus 1. So then you're just going to shift that down by 1 unit. Now, obviously like this, it doesn't really make any sense. It doesn't really look like it's going to be a tan graph. And that's because with the way the shape looks, okay, that full shape is going to be seen from 0 degrees and then 90 degrees. Since our original graph, we can see the shape of the tan graph from 0 degrees to 180 degrees. Okay, so here's where you just need to be creative. You can use your calculator, but the danger with now using the calculator is you're just going to end up with what I have, with these dots and then everywhere else, and then you wouldn't really know what else to put down. That's the reason you need to know what the shape of the tan graph looks like. So the main points we need to catch is where that tan graph, okay, at that 45 degrees, where that tan graph is equal to 1 at 45 degrees. You know that it's no longer going to have this value anymore here at 45 degrees. It will have it at half of this. So take 45 degrees and then divide it by 2. That is at 225 degrees. So in between from 0 to 45 degrees, that is at 225 degrees. This is where it will have a y value of 1. But remember, this is tan 2x minus 1. So that y value of 1 goes 1 unit down, and that's what you're going to have here. So that's that part, and now we can see it's going to go up and move closer and closer to the asymptote. And then also do the same thing on this side. You see how it has a y value of negative 1 at 135 degrees. It's no longer going to have that at this point. It's going to be 135 degrees divided by 2 because of that 2x part. So say 135 degrees divided by 2, and then that's 67.5 degrees. Okay, this one was 22.5 degrees. So that's 67.5 degrees. It's halfway, okay, between this 45 and 90. Now remember how it had a y value of negative 1. Okay, so halfway here we have a y value of negative 1. But then this graph says tan 2x minus 1. So then go down by 1 unit, which would be at -2. Okay, so somewhere down there. And so this is where we get the shape of the graph. The graph, the tan graph, remember it goes from that starting point and then goes up and closer to the asymptote. That is what is going to happen here. Hits here and moves closer and closer to the asymptote. And then from here, it moves like that and down. Okay, so there's the shape of the tan graph. This graph that we can see, the blue part, it just keeps repeating itself all through. So here again, we're going to go halfway through, just like we did here. Okay, so when it was on -1, we went halfway through and then it hits 0. Same thing here. Halfway through, this is where it hits 0. Okay, the x-axis. And then halfway through again, you're going to get an asymptote. Same thing is going to happen here. There, we're going to get an asymptote. So we can put down that asymptote. It is a line down and it's a dotted line. And then again, you see what this graph did from here, okay? And then till that asymptote, it just moved closer and closer to the asymptote. That's what this is going to do as well. It's going to hit there and move closer and closer to the asymptote. So it'll look like that. Okay, so that is that part. Okay, so we don't really need this part anymore because you can see that the full shape of the tan graph is going to be seen from 0 degrees to 90 degrees because they put a 2 in front of the x. So we can't see that full shape from 0 degrees to 180 degrees anymore. So you see the same way this looks over here, we're going to have the same thing going on this side. Okay, so they're from -90 degrees to 0 degrees. We're just going to draw the same type of graph we saw here. Okay, at 0 degrees, you had a y value of -1. At -90 degrees, we'll have a y value of -1. And then halfway through, you have a y value of 0 again. And then this will shoot up, move closer and closer to that asymptote. And then on this side, same thing, okay? We have a y value of -1 here already. And then halfway through, we have that y value of -2, which we can't really see, but it is there. And then this comes from being really close to that asymptote and it moves closer and closer like that. Okay, so we can just put the arrow down. Okay, and then lastly, the same way you can see this shape, okay, of the tan graph as it goes like that, and then like this. This same graph has the same shape, so it goes like this and like this. So what you will have on this side would be this, okay. Okay, so here at -1, then in between, it has a y value of -2, and then it just moves closer and closer to the asymptote we will have here. So normally that asymptote, you will see it every 180 degrees, but because of this 2, you're going to see it every 90 degrees. So we're also going to have an asymptote here from -45 degrees to -135 degrees. We have 90 degrees. Okay, so there. Okay, and this is our graph. It's actually quicker to draw it when you just know where these points are going to be and the repetition that you have in your graph. Okay, but I do find that it does take longer to explain it step by step. So that is our graph. Moving on to the next question. Question 7.3 says graph F is translated 45 degrees to the left to form graph H. Determine the equation of H in its simplest form. Okay, so we create the equation of h of x, by taking the graph of F and then translating it 45 degrees to the left. When we are shifting a graph to the left, when applying this to the equation, because we're going to say we are taking this graph and if you shift it to the left or the right, this is going to affect the x value. Okay, if you take a point, and this is 1 and 2, and you have to shift this point 2 units to the right. From here, it goes 2 units to the right, and it will end up at 3 and 2. Do you see how the only coordinate that changed was the x coordinate? Okay, because shifting a graph to the left or the right affects the x value. So this change would be applied to the x value. And so we're going to say f of, and we're going to say x, and then say whatever happened to all the x values of this graph. So when shifting it to the left, when applying this to the graph, okay, if we are moving to the left, please note that you're going to say plus. So x plus whatever that shift was. If it's moving to the right, you're going to say minus. This applies to when you are applying it to the graph. So because they said it's shifted to the left, we're going to say plus, and it's plus 45 degrees, okay, 45 degrees to the left. And now let's go ahead and apply this. So h of x equals, and you're going to take the graph of f, which we know was cos 2x, and then wherever you see x, you're going to replace this now with x plus 45 degrees because you're adding a 45 degrees to the x alone. Okay, so this says cos, remember that the graph of f was cos 2x. You can't just say cos 2x, okay, plus 45 degrees, because now you've added 45 degrees to the 2x, not to the x. So what you're going to do is when you see x, you have to add 45 degrees to that x. And so you see what this creates. That's why I said it's simply just like replacing x with x plus 45 degrees, since this says f of x plus 45 degrees. Okay, when you see f of x, this is x. This is in place of x. So you just substitute. Okay, and now you can see that you can actually simplify further here. So h of x is equal to, and we have cos, and the 2 will multiply in. So we have 2x, and then that becomes plus 90 degrees. Okay, we have a plus 90 degrees. We can use cofunctions. Okay, remember the cofunction with cos and a plus 90 degrees, or rather 90 degrees plus an angle. This is cos 90 degrees plus a. This will become negative sine a. Okay, so in this case, the a is our 2x here. So h of x would simply simplify to negative sine 2x. And that is our answer. Moving on to the next question. Question 7.4 says, write down the range of h. So this is h. What would be the range of this graph? It's a sine graph and it just has negative. Regardless of whether it has negative or positive, it's specifically a negative one here. Okay, if it was just sine 2x, then this graph, okay, I know that there's a 2 in front of the x. That just means the period has been changed. And instead of the sine graph completing a cycle in 360 degrees, it will complete a cycle in 180 degrees, okay, in half of that. So you'd say 360 degrees divided by 2, like we did in question 7.1. Okay, so this is what the graph would look like. But this is just sine, okay, positive sine 2x. It reaches a highest of 1 and a lowest of negative 1. Now, if you make this negative, it doesn't change the range, okay? What would happen is this graph, all its y values get multiplied by a negative. So this was positive, whatever that was, it gets multiplied by a negative and becomes negative. So it's a negative value here. This positive 1 gets multiplied by a negative and becomes negative 1. So your graph will end up doing this. When you multiply all the y values by negative 1, your graph ends up looking like that, okay? But what still stays the same is the range, because the range refers to all the possible y values that your graph can have. So looking at this graph, look at all the y values. Look at the y-axis. Look at all the y values that this graph has. This point over here, look at the y value. This point, look at the y value. Do you see that it has y values all through from negative 1 to positive 1? It doesn't have y values that are greater than positive 1, okay, because the graph is not up there anymore. We don't have any graph here. And it also doesn't have any y values below negative 1. So we can see that the y values range from negative 1 to positive 1, and we can just say y is an element of, and it goes from negative 1 to positive 1. And then we are going to use specifically square brackets, because negative 1 and positive 1, they are actual y values on this graph. Okay, we have a point with the coordinates that would be 90 degrees and negative 1. Okay, we have an actual point with a y value of negative 1. Same as positive 1, we have an actual point with a y value of positive 1. So you use square brackets to indicate this. Okay, so you can write it like that. You can also just write them as sets. So instead, pull the notation, which is we're going from negative 1 to positive 1. So we're saying y is greater than or equal to negative 1, or less than or equal to positive 1. So you can write it like this or like that, and it is perfectly fine. Moving on to the next question. Then the last question for question 7.5 says, determine the values of x for which, and they say 1 minus tan 2x multiplied by cos 2x is greater than or equal to 0. Now, when you look at this, it looks like at first, they never really ask questions with inequalities, okay, with when you have trig functions. And another thing you need to take note of is, this is the last question. They're not going to all of a sudden introduce brand new graphs. So this definitely has to do with the graphs that you already have. So let's just look at those. Okay, 1 minus tan 2x, cos 2x. Do we actually have these graphs? Remember, we have the graph of, we have tan 2x minus 1. But this one says 1 minus tan 2x. So you can see there's just a common factor of negative 1 there. And then this one says cos 2x. Okay, so cos 2x is the graph of f. So they're clearly using the graph of f and the graph of g, the blue graph. Okay, let's just simplify this further so it actually looks like the graph of g. So remember that g of x was equal to tan 2x minus 1. Okay, so they have just taken out, they've just included a factor of -1 here. We can take it out though. So from here, I'm going to take out a common factor of -1. And then what do we have left? We have a -1, but I want to put it in this same order. So the -1, so if you say 1 divided by -1, I'll put that second. So -1 here. And then negative tan 2x divided by -1, that is positive tan 2x. And this is what we have here. Then times cos 2x is greater than or equal to 0. Then we need to get rid of that negative. You can divide or multiply by -1 and that would get rid of it. But remember, when multiplying by -1, okay, on both sides, this is an inequality. It will cause the sign to change direction. So now what we have is tan 2x minus 1 and then multiply by cos 2x, okay, is now, that sign changes to less than or equal to 0. So what are they asking? They're asking, when you take, this is clearly g, okay, you take the graph of g, okay, g of x, and you multiply it by the graph of f, okay, f of x. I mean, I don't know why I'm putting this in. This should be blue. Multiply it by the graph of f, okay, the one we already had. Then we need to find the values of x for which they will give us a value that is either less than or equal to 0. And that's what they're asking for. Okay, so let's go ahead and pin this to the screen and see where this happens. Okay, so this is what we are looking for. You can see that the graph of g is in blue and the graph of f is in black. We are looking for when you take the graph of g, multiply by the graph of f, and you get a negative value or a value of 0. Let's mark all the places where you multiply them and they give you 0. So if the graph of g had a y value, remember this refers to their y values. G of x stands for the y values of g. Okay, f of x stands for the y values of f. If the graph of g has a y value of 0 and you multiply by any other value on the graph of f, right, for the same x value, of course, it will give you 0. So what we can do is mark all the places where both graphs would have a y value of 0. Graphs have a y value of 0 when they are on the x-axis, because that is an x-intercept. That is where y is equal to 0. So for example, look at the graph of g over here, right? Do you see that it lies on the x? Yeah, so you see why these points were important. It lies on the x-axis over here at 22.5 degrees. This is where it has a y value of 0. So that point as a coordinate, it is 22.5 degrees and a y value of 0. That is the point that we have here. So yeah, grade 12s, you need to know how to draw your graphs at this point. Remember that these, okay, the graphs, you look at that mostly in grade 10, and then grade 11, you start answering questions like this. Then grade 12, they'll take the questions up a bit and then make it more advanced. So I can see that all these in-between points, they might be helpful, but I mean, if they are helpful, we'll take them. Like here, for example, right? We're going to have to find what is in between negative 90 degrees and negative 45 degrees and just put that down quickly. So that was the negative 67.5. I think that was it. Let's just remember. Okay, it is, if you take 45 degrees plus 90 degrees divided by 2, it is that 67.5. So negative 45 degrees, and then this is negative 67.5 degrees. And then we can see this is negative 135 degrees. I'm just looking for all those places where we have 0 as a y value. Over here as well, from 90 to 135 degrees. In between that, we would say 90 plus 135 degrees is 225 divided by 2. Okay, and this is what we have here. It's just going to be 112.5 degrees. I'm just going to keep all of those there because we will need them. Okay, so what I'm dealing with right now is the places where we have the graph of g and f being equal to 0. So do you see the graph of f, right? This graph, where does it have a y value of 0? That is at negative 135 degrees, and I'll put a tick there so I remember to take that. It's at negative 45 degrees, it's also at 45 degrees. This is the graph of G, okay? But then, of course, you'd also have to consider asymptotes. So let's just straight away consider the asymptotes. This 135 degrees, we would have been able to take it, but we can't anymore because there is an asymptote here. So it would mean that this part has an undefined, it's undefined. And then you're multiplying it by 0. It's still undefined, okay? Because you're saying the y values multiply. The graph of f has a y value of 0 at negative 135 degrees, but unfortunately, the graph of G is undefined here. It has an asymptote, so we can't really use that. So let's leave that out. And then where else can we take? We can't take negative 45 degrees. There's an asymptote here, and an asymptote here. We can't take those. Now we can focus on the graph of G. Look for the places where it has a y value of 0. So the graph of G has a y value of 0 here. So we're going to definitely take that. Okay. And then here, and then lastly, here. Okay. We've marked all the places where it has a y value of 0. Now, let's quickly discuss how we can actually get this requirement we're looking for. So when you take the graph of G and you multiply it to the graph of f, it needs to give you a value that is less than 0. We have already marked the places where it's equal to 0. How do you get a value that is less than 0? That is a negative value. So if you take a positive value and you multiply it by negative, you will get a negative value. That is a value less than 0. If you take a negative value multiplied by a positive, it will give you a negative value again. Okay, so we're looking for places where the graph of G is positive, but then for the same x values, the graph of f is negative. That is the first thing we'll look for. Okay, so let's see. Where is the graph of G? Where does it have positive y values? So there are your y values. Positive y values, okay, on the y-axis, they are here, okay, above the x-axis. So whenever you're looking for a positive y value, look above the x-axis. Negative y value, look below the x-axis. Okay, so we're looking for places where the graph of G is positive, but the graph of f is negative. Okay, so the graph of G starting from this side, where does it have positive y values? That would be all through here, positive y values. It's above the x-axis. Now for these same x values, for the same x values that this lines to, as you can see, it's all of these x values over here, values that are basically greater than negative 67.5 degrees and then less than negative 45 degrees. For these same x values, the graph of f needs to have negative y values. Look at the graph of f's y values and where they are negative within that interval. That would be here. Okay, so this actually does happen over here. We can mark this one out. We can say that it happens from negative 165 degrees to, of course, less than this 45 degrees. We'll keep this. This is a valid answer. If we keep moving, we're still looking for where the graph of G has positive y values is above the x-axis. And then for the same x values, the graph of f needs to be below the x-axis. You see what is going on here? The graph of G, the blue graph, it is above the x-axis here. But for these same x values, unfortunately, do you see where the graph of f is? Look at where it is. It is above the x-axis as well. That's not what we want. We want this to be above the x-axis and then this one to be below the x-axis. That way it has positive y values and then negative y values like we had over here. So that doesn't work over there. We can search here. Where is the graph of G above the x-axis? All through here. And then for these x values, is the graph of f below the x-axis? Yes, you see, look at the x values and look at where it's below the x-axis over there. So we can also mark that all through here and then like that. So we know that is also a valid spot that we have there. Okay, so the first scenario where the graph of G has positive y values and the graph of f has negative ones, that we were able to find that. Let's see if this one can be found. Now we're going to look for where the graph of G has negative y values and the graph of f has positive. Okay, so where's the graph of G? Below the x-axis. And I'll use a different color for this. The graph of G is below the x-axis starting from this side. It's below the x-axis all through here. Okay, but then for these same x values, the graph of f must be above the x-axis. It needs to have positive y values. Do you see the graph of f within this interval? Okay, so if you look at this graph, look at the values it lines to. It's all of these values. Values that are greater than 135 degrees, but less than this 67.5 degrees, negative, of course. The graph of f, unfortunately, is negative all through here. Look at the graph of f. See, that's negative y values. It's below the x-axis, so it doesn't work out here, and that's fine. You can just leave that. We're still looking for where the graph of g is below the x-axis, so where the graph of g is below the x-axis again would be all through here. For these same x values, the graph of f needs to be above the x-axis. Where's the graph of f? Look at where it is. Okay, there, it's above the x-axis for all of these values. So it works out perfectly here. And I'm going to mark that out. So it's here, and that goes with that. And then I stop at the same point. It needs to work for the same x values. And then the last place to check is over here. Okay, this is where the graph of g is below the x-axis all through here. Where's the graph of f? Unfortunately, it is also below the x-axis all through from this, okay, from there to here. It's also below the x-axis, unfortunately, so it doesn't work out, and we can leave that. Okay, so you can see all the selected places. The first place is from negative 67.5 degrees all the way to negative 45 degrees. Of course, not at those points specifically. Okay, I just pinned this to the screen so you can see. So with this, I mean, we don't really need that anymore. And so with this, our answer here would be, we would say, this is from negative 67.5. So we're saying x is greater than or equal to negative 67.5 degrees. Remember the reason it's equal to at that point, okay? Because the y value of the graph of g there is 0, okay? And there's no asymptote there. And then, but less than negative 45 degrees. And then we'll say or, and then we also have that working from negative, well, values that are greater than negative 45 degrees, but then less than or equal to 22.5. So you say x is greater than negative 45 degrees, but less than or equal to 22.5 degrees. And then that last part, or, okay, just put those ors so we can see them clearly, or x is greater than, and that was the 112.5 degrees, but less than, greater than or equal to that, okay, but less than 135 degrees. And that would be all the sections where this works out. Okay, so yeah, that is it there. If you guys do see anything that I missed out, please do let me know in the comment section. And that is the last question for 7.5. Grade 12, you know the trigonometry video is always longer than the marks allocated. I do try to do this thing, well, I have been trying to do this thing where I stick with the mark allocation. Like if this is 10 marks, I'll try to take like 10 minutes. But yeah, that doesn't really work out too well because then I miss a lot of things that should be explained. So I have actually just stopped doing that. And so yeah, that's why this video is this long. But I hope you guys enjoyed it. Please do let me know if you do see anything that I may have missed. And moving on to the next question. Okay, and now we're on the last question for trigonometry, question 8. So this is 2 and 3D trigonometry. They say, as part of a school's project, learners are required to design a portable stage for a puppet show. Yeah, I thought this was a soccer goalpost, but okay. As shown in the diagram below. The design must fulfill the following requirements. So BKLC, that's BKLC, right, is a horizontal base having angle KBC being equal to 104 degrees, as we can see, and angle BKC being equal to 52.6 degrees. The rectangular backdrop ABCD, okay, that is vertical to the horizontal base and must have an area of 648 centimeters squared. Okay, so we just have shapes being connected. And then they tell us that the sides of ABCD must be in the ratio AB is to BC is 1:2. Okay, so AB is to BC is 1:2. So for example, if this was somehow like, let's say 11 centimeters, right? Then this one would be double of it. It would be 22 centimeters. So, you know, if you take AB over BC, they would simplify to 1/2, 1:2. Okay, so that's like 11 over 22, which we know is a half. That's 1:2. So that's what they mean by that. Whatever this is double of it. So, I mean, we might as well I'm just going to call this straight away 2AB because I know it's twice the size of AB, twice the length, sorry. length, not size. And then the last thing they tell us is the stage must be partly enclosed with triangular sides, and that is ABK and DCL. Okay, so this is what we have. 8.1 says, show that AB is equal to 18 centimeters. Yeah, I think that's exactly what they were referring to, this 2AB thing. So you see why grade 12s, it can be very intimidating if you just start reading. Because I know that when tutoring, I usually ask learners to read out the question and they'll just straight away start reading. Just reading almost like I asked you to read out a story. You're supposed to read and just start visualizing what is going on. As you're reading, you're pointing out what is going on, and that way you keep track of everything they're saying and it doesn't get intimidating. This info is a lot of info. It looks like it's complex. It's not. You see that from this, okay? We can see now that BC is twice the length of AB. So it can be called 2AB. So how do you think you would be able to find the length of AB? Seeing that in this shape, there are two lengths that are in terms of AB. Okay, here's what we have. We have this. The shape is a rectangle. And this rectangle has a length of 2AB. Okay, because they told us AB is to BC is that. So we can basically tell them, oh, okay, so that means that BC is really 2AB. And so they gave you 2AB, and this is AB, but they also gave you the area of the shape. How do you find the area of a rectangle? You say length times breadth. So we know the area already is this. And so we're going to say, okay, the area is equal to the length times the breadth, but we know that BC is the length, and we can call that 2AB. And we know that this is the breadth, and we can call that, that's just AB, okay? And the area itself is 648 centimeters squared. So this is what we're going to use to solve for AB. So 2AB times AB equals 648 centimeters squared, okay? So here, what we can do is multiply. That gives us 2. AB squared is equal to 648. Then divide both hand sides of the equation by 2. And so AB is equal to 48 divided by 2 is 24. And so that's 324. And then that's AB squared, of course. And then you can square root both hand sides. And what is the square root of 324? Square root of 324 is 18. And there we go. And that's how we find that. And so we can just tell them AB is equal to 18 centimeters. And that is our answer. Moving on to the next question. And then they say 8.2, calculate the length of AC. Let's see where AC is. AC, okay. AC is a diagonal. Okay. How do we find a diagonal if you are given a rectangle? Well, if this is a rectangle, it means the corner angles that they are equal to 90 degrees. Okay, so we know this is a rectangle. Okay, I should have already said initially, they said rectangular backdrop. Okay, so we know it's a rectangle. And we're going to find the length of this. And we're going to find AC. And we can just use Pythagoras because this is a right angle triangle. And so here's AC. We're looking for AC. We have AB. And so, of course, we will know what 2AB is. We know the length of BC. So let's just fill BC in. So we know that BC is 2 times AB. And so therefore, that just means that BC is equal to 2 times 18 is 36. So 36 centimeters. And we know AB already is 18 centimeters. So using Pythagoras to find AC, you're going to say AC is the hypotenuse. So AC squared is equal to, and you're going to take that AB squared. I mean, you can write the full thing out if you want. It's not necessary, but yeah. We don't need reasons here. It's 2 and 3D trick, not Euclid. So we're just going to say AC squared equals, and we say 36 squared plus 18 squared. And then let's quickly find that. Okay, so AC squared equals 1620. And then square root both hand sides of the equation. So you don't have to consider any negatives. We're working with lengths. So AC is finally equal to, and let me just get that, square root of 1620. That is in decimal form. I don't think they want us to leave it as a third. Well, I'll leave the third form answer first. So 18 root 5, and then finally just say AC equals and round off to 2 decimal places. So 40 point, and that 9 is going to round the 4 up to a 5, so 25 centimeters. And that is the length of AC. Okay, moving on to the next question. Then question 8.3 says calculate the length of diagonal KC. Okay, let's just see where's KC. AC is over here. Now we're looking down here. Okay, so you see the way you find AC, it's not the same way you would find KC. And the reason why is because this is not a rectangle. As you can see, corner angles are not equal to 90 degrees. But we can still find it because this is KC over here. And look at how we can find KC. You have been given, okay, if you look at the angle right opposite this side KC, you have 104 degrees. And then we also have this, okay, it's 2AB, but it's actually 36 centimeters. We already have that. So we can find the length of this using the sine rule. So, okay, we're looking for this. We have the angle opposite it. We already have this angle and we have the side opposite it. So because you're looking for a length, I'm going to put the length first. So we're going to see this as KC over sine of the angle it is opposite, which is 104 degrees, is equal to, and then you take this BC, which is 36 centimeters. So 36 centimeters over, and then sine of this 52.6 degrees. Okay, so 36 centimeters over sine 52.6 degrees. And now all we have to do is solve for KC. You see that to get KC alone, we need to get rid of sine 104 degrees. It's saying divided by this. So to get rid of it, you'd multiply by it. So what you do on the one side, you must do on the other side. Okay, so multiply both hand sides by 104, sine 104 degrees, and that cancels. And so we have KC, and then is equal to 36 times this, it's in the numerator. So we have 36 sine 104 degrees, and then all over sine 52.6 degrees. Okay, so KC is equal to, and just put that into your calculator and you can get your answer rounded off to 2 decimal places. Okay, so our answer for KC is 43.97 centimeters, and that is our answer. Moving on to the next question. And now we are on to the last question for trigonometry, and for question 8. We have, if AB is equal to BK, calculate the size of angle KAC. Okay, AB equals BK, find KAC. Let's see. So they're saying AB equals BK. Okay, so we know that AB was 18. So this is also 18. So we have a little isosceles triangle there. But it's clearly not the point. They want us to find this angle KAC, this angle. Okay, do you see how they created a triangle? Okay, we're telling us to find certain diagonals. They created this triangle that we can see up here. So this is the triangle I'm referring to. And in this triangle, what we have, let me just make this smaller. So 36 centimeters, we don't really need that. It doesn't seem like, because it's on the bottom. With this, look at what we have. If we have this, okay, and this is a right angle triangle, we have 18 and 18, we can find the hypotenuse. We also have KC and we have AC. Okay, so they want us to find this angle. Yeah, we can use the cos rule here. So this triangle, the sides you already have is AC, you have KC, you can find AK, and then they want you to find this angle. So we can use the cos rule because we have the length of the side right opposite that missing angle. Okay, so let's go ahead and do that. I'm going to take the shape down and let's find what we need to find. Okay, so the first thing we clearly need to find is AK. Let's find AK first. You can see that this is 18, this is 18. We have a right angle triangle. We can use Pythagoras. So to find AK, we'll say AK squared is equal to the 18 squared plus the other 18 squared. And then I can just find that first. Okay, so we have AK squared is equal to 648, and then square root that. So the square root of 648 is, okay, AK squared. I'm just not going to round off yet. Leave it as 18 square root 2. I'm just going to leave that. AK is 18 square root 2. And now let's go ahead and find that using the cos rule. So if this is 18 root 2, how do we use the cos rule here? Let's just put down what we have. We know KC, and we'll take it like this. Since this is one of the things they actually ask for, you don't have to use the unsimplified form. So this is 43.97, and we already had AC, which was 40.25, right? 40.25, and now we can use the cos rule. So with the cos rule, just a quick run on that. If you are given a triangle and you are given the following size, let's just say this was 8 units, so 9 units, and let's make that 11 units, right? But you needed to find this angle. The cos rule works like this. Let's say this side was C, this was A, and this was B, okay? So you would say C squared is equal to A squared plus B squared minus 2AB, and then cos of the angle right opposite C, which is this angle. And let's just say that point was C, okay? So it will be angle C. And with this equation, we can just isolate this cos angle C and then solve for angle C. Okay, so that's what we're going to do here. Okay, so let's take this and let's see what we have. We're taking this side, okay? So that is KC all squared. KC all squared, because it's right opposite the angle we're looking for, is equal to, and then we take this side squared, which is AK all squared, plus this side squared, which is AC squared, minus 2 times AK times AC, and then cos of that angle, which is the angle they're referring to, KAC. Okay, so cos of angle KAC. And let's just substitute. So KC all squared, that was 43.97 squared. And so you just need to be careful here. Is equal to AK, that is 18 root 2, not rounding off, and then plus AC, that was 40.25 all squared, then minus 2 multiplied by 18 square root 2, okay, AK times AC, which is 40.25, then cos that angle we're looking for, and we will just solve for that angle. So with solving for the angle, let's just check and look for the amount of terms we have here. So on the right hand side. On the right hand side, remember that terms are separated by plus or minus signs. So wherever you have brackets, they join terms together. So what we have here is a plus, a minus, and so you can see you have 1, 2, 3 terms. But these two, they're just numbers. You can actually add them together. So that's what we're going to do. We're going to add these two together first. Okay, and this is what we get, and I'm not going to round off. So I'll leave it as 2,268.0625, and then I'm going to get this one. So if you say 43.97 and you square that, what do we get? We get 1933.3609. Okay, so like that, and then we need to just get all of that. So with these ones, just multiply your numbers together first. Notice that they're going to be negative. Okay, so what we get there is a negative 2047 point. Yeah, I should not round off with this one. Okay, so how you multiply this is important. What you can do is just multiply. I'm going to say the negative 2, okay, first multiplied by this 40.25. And so we get this, right? Then multiply by the 18. And then that way, this is what we get, times 18, okay? We get negative 1449, then square root 2, okay? So there, all the numbers have been multiplied. That with the negative 2 and then the 18, okay? Because we shouldn't have decimals yet, since we still have to, solve for that angle. Okay, so this is what we have. Now, I want you to see what is going on here. Here, the number is negative. You can't just make it positive by taking it over. So one time, if you just take it over, it is 1449 square root 2 cos angle KAC. Then what happens here is this is already on the right hand side. Just go ahead and transpose this one. Take it over and it will become negative. So it's this minus that number. Okay, so we get 334.5 0.7016. Okay, and now look at how we can solve. We're trying to get to this. Okay, so this is in the way right now. So you can simply just divide both hand sides by that number, and then we get cos angle KAC is equal to, and I mean, for the sake of just keeping this simple, let's just leave it like this. I'm not going to put it on the calculator. Now we are trying to actually solve for this angle. So now to finally solve for angle KAC, we can transpose cos. And so angle KAC, since we are working with a triangle, which has all the other sides, and then we're just looking for that missing angle. Okay, so I was just checking if it could possibly be that ambiguous case, but they don't bring that up a lot. Actually, I've never seen them bring it up in an exam. So let's go ahead and find this. So on your calculator, you're just going to say shift cos, so the second function of cos, and then put down this value. So it's 334.7016, and then over 1449 square root 2. And this is our answer. Okay, so the angle, the size of this angle is simply 80 point, and yeah, you can see those. They're going to eventually round that 5 up to a 6, and it's just going to be, you can just say 80.6 degrees, and that is your answer. Okay, I'm just leaving it, the way they left this one, for example. One of the angles that they gave here had a 0.6 degrees as well. So that was this. So I'll just leave it like that. Okay, so that is our answer. That is it for the trigonometry section. The 2 and 3D trig was actually really nice. They, went step by step, just asking for certain things that they knew that you needed for that final question. Okay, so that is it for trigonometry. And I will see you guys in Euclidean geometry.